we found that the parameter values are equal to the inverse S matrix times the inner products of trial vectors and data values. Now, for a single value of A, the values psi sub alpha A, which is trial vector A, can be thought of as a single trial vector, and all of them together make up a set of trial vectors. I'm going to use the inverse S matrix to define a different set that I'll call the dual trial vectors. They are defined as dual trial vector A is equal to the inverse S matrix times the trial vectors. Now that's why there was a dagger on the psi I used in the last lesson. With this particular definition, where I define the dual trial vectors to include the product of the inverse S matrix and the trial vectors, I can simplify the definition of the parameters by just saying that parameters are equal to dual trial vectors inner product with data values. Now, the dot product of a dual trial vector with a trial vector, they might be different ones or they might be the same one, is given by the dot product of dual trial vector, that's this inverse S matrix times trial vector, with trial vector. Note that I used J for the dummy index so that I wouldn't confuse it with the A or the B. J is just a dummy index, it's just for summation, it's just for indicating where things get summed. However, this part of this equation, psi sub alpha j, psi sub alpha b, an implied summation over alpha Einstein summation convention, that's just the definition of the S matrix. So this turns out to be S matrix inverse times S matrix. And that's going to be the identity matrix, which I've written as delta sub AB because delta sub AB is the Kronecker delta, also known as the identity matrix. So I have the interesting property that the inner product of a dual trial vector with a trial vector gives you a component of the identity matrix. If they're this corresponding vector and dual vector, gives you 1. If they're not, they give you 0. That, by the way, is the actual defining property of dual vectors. So that's why I called them dual trial vectors. Another thing worth knowing is what if I take the inner product of a dual trial vector with another dual trial vector? Might be the same one, might be different ones. In that case, I have inner product of dual trial vector with dual trial vector. And I can look at these two terms and see that the summation over alpha defined by required by the Einstein summation convention can be factored out of the other products, but that summation is just the definition of the S matrix. So what I get is that the inner product of a pair of dual trial vectors is inverse S matrix times inverse S matrix, which is just going to leave me with the inverse S matrix. Now, this whole thing really amounts to something that can be thought of as projection. The set of all possible data values is a set of n numbers if we have n data values. We can use this to define an n-dimensional vector space. I call it sampling space. And we can show, if we wanted to go into all the details, that it has all the properties that are required to call it a vector space. It's an n-dimensional vector space because there are n independent quantities required to define a point of it. Now, the set of all possible models, which is parameters times trial vectors, that's an r-dimensional vector space because we consider the trial vectors to be fixed and we allow the parameters to roam freely, so we only have r degrees of freedom for that possible set. I call that r-dimensional vector space model space, and each model corresponds to a point in sampling space. It's the point if all the noise values were 0. So model space is a subspace of sampling space. Now, the residual vector, what I get if I take the data values and subtract the model values, it's the part of the data values which is not in model space. And when we minimize the sum of squared residuals, we're really finding the point in model space which is closest to the data vector, because the sum of squares, that's the definition of Euclidean distance. As a natural consequence, the residual vector, the part that is not in model space, is orthogonal to all of model space, and therefore it's orthogonal to every one of the trial vectors. That is to say, the inner product of the residuals with a trial vector is equal to 0 for all trial vectors. Now, if we used a different set of trial vectors, which happen to span the same model space, we're going to get the same projection because we're projecting our data values vector into the same subspace. Ultimately, the projection we get, the model we get, it depends on the subspace spanned by the trial vectors, not on the particular trial vectors that we use as a basis for model space. So if we use two different sets of basis vectors, of trial vectors, but they span exactly the same space, then we're going to get exactly the same projection, and it'll have the same properties. An example is this. Suppose we're doing linear regression, and we change the 0 point of time. Well, then the time vector is different because we've just subtracted a constant from every value. So the trial vectors are different. But the model space is the same. So we get the exact same model, which tells us that if we're doing linear regression, it doesn't matter where we choose as our 0 point of time. We're going to get the same straight line model no matter what. It's worth repeating that the n data values define a vector in an n-dimensional space. I call it I call it sampling space. The least squares regression is equivalent to projecting that vector onto the r-dimensional subspace spanned by the trial vectors. The residual vector is orthogonal to that subspace, and therefore orthogonal to the model we get, as well as orthogonal to every one of the trial vectors. Now, if there are r equals n trial vectors, so the number of trial vectors is the same as the number of data points, and if they're all linearly independent, then the trial vectors are going to span the entire space of all possible data values. In that case, projecting the data vector onto the entire space of all possible data values, which is what we'd get from least squares regression, it's going to leave it unchanged, so the model will be exactly the same as the original data vectors. The model will fit perfectly. The residuals will all be 0, and we will have the ultimate case of overfitting. Of course, the model will fit perfectly because we allowed it so many degrees of freedom it can fit every data value. Even when the number of trial vectors is less than the number of data values. When we get enough trial vectors, when R gets big enough that our model can fit much of the noise as well as the signal, and that's the real problem with overfitting. When you have so many degrees of freedom in your model that your model ends up fitting a lot of the noise, not just the signal.